Hello, everyone, and thank you for joining us today. Welcome to Megger's monthly Testing Tactics webinar series. Today's topic is Cable Testing 101, Introduction to VLF Testing. My name is Greg Valdez, and I'm the Marketing Manager for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NEDA CTD and one PDH or 0.1 CEU for attending. You will receive this in an email within 2 business days of the webinar. That email will also include a copy of the PowerPoint presentation and a link to the video recording of this webinar, if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Robert Probst, Cable Product Manager. Also, to assist with the question and answer session, we will also have Jason Suchek helping us out today, who is one of our technical application engineers. All right, let's go ahead and get started. Thank you for joining us today, Robert.
Good morning, everybody. So I'm glad that we have the chance here to do this webinar on VLF testing. As you can see on your screen, this will be part 1 of a webinar series on cable testing and diagnostics. And today, part 1 will be the VLF testing. Then scheduled for April will be part 2, dealing with PD diagnostics and how PD diagnostics would interface with the life of the cable and the life management of the cable. Then in December, we have part 3, which completes the circle with the loss factor diagnostics, 10 delta diagnostics. And in between, we will have one fault locating webinar, which as of now, I think Henning will be doing that. Okay, so today's agenda is pretty intense, a few topics. But still, it's a 101 webinar, so we will do this, as an overview. We won't go too deep into the physics and chemistry and everything. So first of all, I just want to bring everybody on the same page and talk about how did the power cable infrastructure evolve very briefly. Then we will be talking about this whole testing and diagnostics approach. What is the objective and the motivation for that? Keep in mind, since this is a 3-part series, some things apply to VLF and some things are there because they are true for 10 delta and PD, which will be in the next parts. Then we will be talking about what is VLF testing by itself. Then just briefly about the aging mechanism in solid dielectric cables. Then the test standards will be mentioned. We will be talking about the wave shapes. I will have 2 examples for the effectiveness of the VLF testing, and then at the very end, we will have an outlook to the diagnostics, which then will be covered in part 2 and part 3. Okay. So the way this whole thing started was in the 19th century with distribution using cable, and initially there was only laminated type cables, which means either paper mass cables in distribution, so locally, and then later in the 1920s, the oil-filled cables. So 1890 is pretty much the year where the first real single-phase AC cable was made, and 2 years later, they made the first 3-phase cable. And all those cables, the 3-phase cables, were belted cables. So belted cable means that you have a 3-core cable with a lead sheath lead cover on the outside typically. So this is why a lot of people call these cables lead cables. And belted cable means each individual cord does not have an individual screen. So there's one common screen for the three phases. And in terms of fault locating, that makes it very complicated because you can have face-to-face issues. And another problem for the cable infrastructure was these belted cables were not able to exceed 20 kV. So for many years, distribution was limited to 20 kV, and the solution came from a German high voltage engineer. He put a metal foil, a perforated metal foil around each of the cores and turned the belted construction into a screen construction, and that was the big breakthrough which started this kind of, progression in voltage class. And the H cable was a paper mass cable that could exceed 20 kV. It got into problems around 60 kV. So when you were getting into the 60 kV range, then the H cable, named after Professor Höchstädter, got into trouble as well, because then you had PD issues. And then working for Pirelli, Luigi Emanueli invented 1927, well, a few years earlier, but in 1927 it was presented to the world, the first ever transmission cable, oil-filled, oil-pressured cable. So then in the 1940s, the plastic technology evolved quite a bit. And in 1940, the first solid dielectric cable was manufactured. However, there was not a big breakthrough or anything. It was just there. In the 50s, there was a lot of, PVC put in, which haunts us today because PVC is a terrible insulation material for cables, high losses, and should not be used anymore at all. And then in the 1970s, the big shift happened. So the PILT was drastically phased out in Europe, at least, and relentlessly replaced by solid dielectric cable. And that started this whole learning by doing approach, because with each cable generation, they fell on their faces because they learned something new that wasn't known before. And until they arrived in the 1990s with the third, or whatever you want to call it, fourth generation solid dielectric cable that is now, the state of the art. However, very interestingly, the same change did not really happen in North America. It's actually very slow change. You still have a lot of PILT in the NAFTA area in the US, and specifically also in the transmission area, the 345 kV levels and higher, which internationally is all XLPE these days. You still have probably, I would guess, at least 90%, probably 95% oil-filled cables. And all the traditional methods, they were all tailored to these laminated cables. And now the question is, now we have all solid dielectric cables, XLPE, EPR. So what is this traditional testing doing on these cables? And that situation was unclear and got kind of investigated and resolved over the years. So this is how it happened. So we went from paper mass and oil filled to XLPE mainly, and in North America a little bit EPR, because here EPR is for some reason more popular than in the rest of the world. Okay, so what is the whole objective and motivation for cable testing and diagnostics? So the main task or the main interest of the utility companies were, we need to leave our run to failure reactive maintenance approach or asset management approach. We need to be proactive, and we need to apply scientifically or technically sound methods to obtain data, which we can then use to make educated decisions. So they started doing this cable testing and establish these cable replacement programs. And to increase reliability means then to reduce outage minutes, which is directly tied to the budget of utilities internationally speaking, which is also tied to the fact that many countries apply a structure of high fines. When you have outages, then you have to pay out directly to the end customer. It's very common internationally. For instance, the Netherlands have this model where you not just having an impact on your safety and SAIDI, but then for every outage minute, every single customer gets a check for that as a compensation. So, you know, to reduce the outage minutes and to have the reliability go up, you then establish a habit of proactively looking after the cables, monitor any conditions, repair them in time, or replace when there's no other option. And that ties into the big field of asset management. So cable testing and diagnostics is not really there to have an immediate action. You know, you want to learn, or at least you want to prevent and avoid any critical emergency conditions that suddenly, you know, the circuit fails. But in the long run, the asset management is after allocation of resources, and every utility has budget restraints and constraints. You want to use a technical and systematic approach to gather your data to make these investment decisions. And at the end, asset management here means to establish a successful cable replacement program. And as you will see, VLF testing is one of the 3 cornerstones to do that. So the holistic strategy is, how do I increase the reliability of a circuit? Well, I look at the total life cycle of the cable, and that begins with the cable is installed. I need to do an acceptance test. At the end of the cable's life, replacement of sections, vast sections, or the entire cable is inevitable. And in between, there is the key. There's the key to make this work and to maximize the lifetime of the asset. It is periodic maintenance testing. So then for the VLF testing itself, you have mainly 3 applications, so to speak, 3 application fields. So first of all, let's say you worked on the cable, or a crew worked on the cable. You can use this as a simple workmanship test. You put the high pod on, and after repair, after you spliced, after you put on new terminations, just to see that it will hold voltage and you can energize. The main tool, however, is the preventive maintenance. So the periodic testing of the circuits to weed out the critical defects. And we're talking about local weak spots, nothing global. And then as a variation, you can also do some predictive maintenance with the VLF test if you conduct it as a so-called monitored withstand test. And then you're doing the fully standard compliant VLF, and you add a condition assessment, like a trend indicator, which there's 3 trend indicators, and leakage current, partial discharge, and 10 delta. And then depending on in which stage of the cable's life you are, not all of them make sense. Like for instance, during acceptance testing, 10 delta is absolutely useless and nonsense. You even get incorrect readings. A few months ago, I had an expert seminar with some of our customers in Slovakia, and they don't do 10 delta testing for the first 7 years after installation, because you will get misleading 10 delta readings, because there's no water in the cable. It's a new cable. It still gases out. You have these chemical settling processes in the insulation. So their experience is, if we start doing 10 delta after 7 years, then we're okay. But that is already in the service aged stage. So for acceptance tests, VLF and PD, and then for the service age cables, different set of technologies. But with the VLF test, and you use a trend indicator, you can gather and learn more that allows you to actually have predictive data. And now the difference in these applications is you have the withstand test mainly as or the workmanship test, and then the monitored withstand or the preventive test. And this is just, you know, a rough overview. Obviously, a workmanship test, you just put on rated voltage to see what it holds, and the purpose of it is, It doesn't fail after you have touched the cable during, its normal service life. The main thing is that doing the repeated periodic maintenance by standards, and we will get to these numbers later on. So it varies from 1.7 U-Not, which is the operating voltage, to 3 times, and this is really to find local defects in the cable insulation and somewhat splices and terminations, and typically done at 3 times U-Not. So now, just as a comment on what you gain with VLF, I phrase this here as you always win with VLF, because when the cable passes the test, based on the international data that we have since like many decades, you gain a statistic reliability of 97% that the cable from internal failures will not fail within at least 2 years, typically even 3 to 5 years, you can say. And if the cable fails during the testing, well, you need to be prepared. It's a proactive approach. So you better have your cable fault location equipment ready, means of bypassing the circuit or replacing the section of the cable or the entire cable. But you found a critical weak spot that would have caused an in-service failure, an outage, a true outage, and you found this in controlled circumstances during a planned outage for doing the testing on your circuit, and you prevented an in-service outage. So this is a win-win situation. Regardless of what you do with VLF, you have a overall positive outcome. Now there's certain test standards, mainly international. So you have the very top one is the strictest of all. It's the German standard. Then you have the European standard, which is pretty much following the German standard. You have the IEC standard, which is following the European standard. And then you have the IEEE standard, which is its own thing, so to speak. So when the IEEE standard was conceived, all the experiences and the knowledge from the other 3 standard groups, which pretty much covers the rest of the world, were kind of pushed aside, and IEEE decided to go its own way. And you will see this later, what I mean by that. So these standards pretty much have very clear requirements. First of all, VLF voltages are always given in RMS. They are related to U-Not or V-Not. It's the definition of the operating voltage of an asset in the power industry, which is the line to ground voltage. So that's the voltage that the main insulation of the cable sees. And for VLF, it's 3 times U-Not, pretty much across the board, and testing time 60 minutes. And then I made this comparison, which I understand is a little bit, convoluted, but stay with me here. So I broke out the voltage ratings of the cables on the left. So I just chose, okay, a 10 kV cable, because internationally 10 and 11 kV cable is the most common cable in the world. Then 15 kV, which is very common in North America. Then 20 kV, very common in Europe, Middle East, and everywhere. 25, again, a North American level. 30 kV, again, more of an IEC level, and then 35, again, more of a North American level. And if you look at the 3 main testing standards, testing values to determine testing values is very easy, because you go with RMS. There is no influence of the wave shape, because for every wave shape, you can define an RMS. And these standards are written in RMS, and you say, I do 3 U-Not, and that is pretty much your testing voltage. And for any waveform there is for VLF testing, and the frequency, very important, is fixed. In the IEC world, you are not allowed to reduce the frequency from 0.1 hertz. And in IEEE, you can see it takes more than half of the table, and this is only the acceptance test. There's also in the IEEE 400.2 table 3, where all these numbers are stated, there's then also an installation test and a maintenance test, which has different values. And you can see those values in IEEE differ drastically from rest of the world. Specifically, there's a difference in wave shape. Not all wave shapes are, treated equally here. The frequency can be reduced. If the test set cannot charge the cable properly, the testing time is slightly different. And so this is pretty much the testing values that are applicable. And you see, when you compare the PU values per unit, which means you compare the test voltage against U naught, the operating voltage of the cable, you can also see that rest of the world is cookie cutter, 3 times U naught. And in IEEE, there's a fairly complicated test table, table 3. Now, why do we even do AC testing? What was, and that ties into this change in cable infrastructure? Well, the DC test, the classic DC test at very high elevated test voltages, 5 times operating voltage, 6 times operating voltage, that was for PILT cables, for laminated insulation. And the question was, is this applicable for solid dielectric cables? And as it was found by the scientists, no, it is not. The DC testing is actually damaging the solid dielectric insulation, EPR and XLPE. So this is why it's not recognized anymore, not in IEC and not in IEEE. There is no DC test standard for years now. I mean, we're talking about a good 10, 15 years now since DC testing is banned in North America and even longer in the IEC world. So DC testing still okay on PILT cables, even if I would still do a VLF on the laminated cables as well, and definitely don't do DC testing anymore on solid dielectric cables. And then there's another thing on top of that, that result with that the DC test is damaging the insulation, which is, by the way, called the space charge effect. So because DC is a unipolar voltage, you're pumping the insulation full with charge, and this forms space charges, concentrated, amounts of charge which are trapped. And even if you properly discharge the cable, you will not be able to evacuate to discharge those trapped space charges from the solid dielectric insulation. And the main reason for that is, just as a technical background, when we're talking solid dielectrics like polymers, polymers are chain molecules. And now many people assume if you have these chain molecules, everything is in order and everything is straight and looks really nice. The truth is, on the molecular level, it turns more into, spaghetti on your table. Like, it's not so straight anymore, and you have, like, not all the molecules are orientated in the same direction. And so you have pockets available there. By the way, also, these are the pockets where the moisture can come in and stay in the cable. And this is exactly where you trap these space charges. And then when you re-energize with AC, power frequency, the cable will fail pretty soon, because in one direction of the polarity you will have over voltages, and then immediately you created a partial discharge weak spot in the insulation. Now, a result that wasn't really expected by the people working on investigating these first, second, third generation polyethylene cables. They also put the different voltages up to the test if they are able to find faults or, fault conditions. And the result is stunning. As you can see, the DC test scored 0 out of 12, both on the XLPE cable and the PILT cable. And the expectation was, well, it should be effective on the PILT cables, right? But it was not. And you can see at those levels, I mean, those are insane test levels. 8 times operating voltage. Just imagine that you have a 15 kV cable that has an operating voltage of 8.7 RMS. You do 10 times operating voltage. So you tested this cable with 87 kV. And for 30 minutes, and it did not find this needle fault. And so it was very surprising for many people that even on the pill cables where DC testing was the test, was also kind of ineffective and was blind to many defects that can actually occur. So if you go to any AC test, doesn't matter which one, you can see they always scored 100%. So this is what's considered the blindness of DC testing. So it's not only hurting and damaging the solid dielectric cables, it's also ineffective in terms of seeing and identifying certain fault conditions. So, and then when we say aging of these cables, so there's in solid dielectric cables, it's a little different in pill cables because there you have cellulose degradation and drying out, carbonization of the oil and the mass and everything. But in solid dielectric, both in XLP and EPR, the main aging mechanism is treeing, water treeing. So what is water treeing? As you can see, you get these three-dimensional structures filled with water. By the way, if you ever cut a cable open, it does not look like that. These are samples where they put an indicator fluid to color the water pocket. Otherwise, you cannot really see the water trees. In some cases, when you cut the cable open, you can see maybe small white dots along the insulation, but that's pretty much it. And then if you see that, if you cut it back and the insulation, seems to have, you can look through it and you see these few white spots, then it's already contaminated and in a very bad condition anyhow. So, but these are these treeing phenomena. So you need three ingredients to have them. You need the presence of AC voltage, moisture, which sooner or later will be in the cable, and time. So just to give you a ratio or a relationship, the water trees typically take years and years and years and years to grow, decades, while as soon as the water tree converted to an electrical tree, that is very quickly. We're talking at operating voltage weeks for the cable. So once you have converted from the water tree to the electrical tree, the cable is doomed. And then again, a comparison, the water tree, you have different types. You have the typical vented tree, like in the left. In this case, by the way, it's a, almost uniformly aged cable. So that's not really critical. While the picture on the right there, this big single water tree, that is a real critical water tree. And on the right, you can see the electrical tree. So that is a, that at the end, it provides a carbonization path, and it will, the cable will fail as soon as the insulation is bridged to the other electrode, to the low potential, to the shield, which is bonded to ground. Again, another nice picture. So this is an XLPE where you see the water tree started at a protrusion, an imperfection of the semicon layer that is smoothing the electric field around the center conductor. And then once the water tree reached a critical length, the field distortion was so high that an electrical tree was created, and that flashed over the insulation. And why does the water tree cause this effect? Well, you see on a new cable or an undamaged serviced age cable, so no water tree damage, the electrical field is very uniform, nice, homogeneous. So there's no distortion, but the water tree, because it has, there's a material related parameter that is called permittivity, which is kind of, permittivity is causing field to be displaced, compressed, or, displaced out of a certain volume. And because water is very different in its permittivity than XLPE or EPR, you get a field distortion, a concentration of field, and this is when the local breakdown strength of the solid material is exceeded, and then you create an electrical tree is created. So one other comment, because you saw in the one table 60 minutes, 30 minutes, whatever you do, never compromise on the testing time. Because once you apply the VLF voltage, and it is stressing the insulation, and the water trees are sitting there, and then electrical trees are formed, or existing electrical trees are accelerated. This takes time. Initially, when VLF came to North America, after it was already established for over 15 years in Europe, there was kind of a little bit of an outrage from some people, because they applied it and they had more cable failures after VLF testing than before. So they were like, oh, VLF test is bad for the cable. And then further investigation, asking a simple question. So how long did you test the cable? And they said, oh yeah, we just did 10 minutes and then we stopped because the cable would hold the voltage. Well, this is exactly wrong, because you started the acceleration process of the electrical trees. And just to point this out, and I'm sometimes guilty of that as well, in the heat of the moment, sometimes you misspeak. The VLF test is doing nothing to the water tree, essentially, more or less nothing. So if the water tree doesn't have a critical length, or the many water trees that you typically have, just to get this misconception out of your heads, when we're talking water trees, it's typically not a single water tree in a certain volume of the cable, a certain section of the cable. It's many, many, many hundred water trees over a bigger volume, and also many, many hundred electrical trees. And which one is the critical one? Well, the VLF test is the only test that can actually tell you, because then it will make it flash over during the test. So we're not talking one single water tree or electrical tree, but once you start this process and the insulation is stressed, and then you have these electrical trees and they get accelerated by the VLF, if you stop prematurely, you're impacting your cable very negatively, because then you energize again, you started the acceleration process, and you stop before you actually could give the test enough time to really say, okay, yeah, this electrical tree would have failed after or within 60 minutes, and this is how you missed it, and then you re-energize, and a few weeks or months later, you got an in-service failure. So you need to do the test for the proper testing time. Never cut short on the testing time. That's one of the biggest mistakes you can make. And then here is the first, example. So these VLF test values, specifically the international ones, there was one big study conducted in Germany, in the city of Dortmund Energie und Wasser, the local utility, and they said, okay, HDW, we will get to this in a second, that was the manufacturer, we believe in your VLF technology, but you have to prove it, and we are willing to be the guinea pig, because, they had a gain too, the manufacturer that invented this technology could statistically prove the effectiveness of the technology, and the utility got a free testing regime for 10 years, and then provided a test report. So Dortmund was willing to have their entire cable network tested, many thousand miles of circuits, many hundreds of cable circuits. And when you look at the distribution of failures, you see that still in the second 30 minutes, 25% of the failures occurred. So if you stop at 30 minutes, for instance, at a serviced age cable, it's not so critical on an acceptance during an acceptance test on a new cable, because those cables are typically not severely aged and damaged in terms of the main insulation, but on serviced age cables. And then when you would stop prematurely, then you also don't get the statistic reliability which came out of this study. These 97% for 2 to 3 years definitely come from Dortmund. And then one of the biggest things is pretty much that some people would always consider VLF testing as a destructive test, which it is not. I repeat, VLF is not a destructive test, because there's two types of AC hypot test. There's the withstand test, and then there is the step test. The withstand test has the intention of you apply the voltage, and it's a pass or fail test, go, no go test. And the step test is really bringing the insulation to its limits to see what the actual remainder of the breakdown strength, remainder of the life actually is. So the intention of the step test is to fail the sample. The intention of the VLF test, or the withstand test, I should say, is not to fail the cable. But here's the trick. If you have defects in the cable, the test will fail them. It will not introduce new defects. So VLF is not damaging the cable, but it will grow any weak spots and then fail these critical weak spots during the test. So if you don't have any existing weak spots in the cable, the VLF test will pass. And you will see in the second study I brought with me, and we will elaborate a little bit on those values, that you can see that VLF is a non-destructive test. Again, the destructive test would be the step test, and there's also procedures for that and standards for the step test. There's an IEEE procedure and an IEC procedure, which is a bit different. So then another thing is VLF test. When people hear the test value 3 times operating voltage, some people they think they overstressing the insulation. So first of all, if you look at this diagram, bear with me, I will explain it. So you have the breakdown strength here of the undamaged cable, and then this other line that starts over here. I hope you see my mouse pointer, that goes down here. That is the damaged service age cable. So that has water tree in it. So you can see, first of all, big difference in breakdown strength. So if you have water in the cable, water trees, your breakdown strength is reduced. But as you can see, this curve is frequency dependent. So if you are worried about VLF testing, you better worried about your 60 hertz test sets or whatever you do at power frequency, because you see the margin, so to speak, the safety margin is much, much less at power frequency than at VLF. So, if you think that VLF is overstressing the cable, then look where you end up at the 60 hertz, okay? So just to get this misconception a little bit addressed here. And another thing is, as you can see, because the damaged cable, this curve also means at 0.1 hertz, when you see this, that VLF is a proper test to finding these weak spots, because you can actually make them flash over with a fairly reasonable test voltage, much less at least DC. And also when you go down in frequency, because over here you're approaching DC, that also corresponds with the experience that the industry has, that for DC you need much, much, much higher test voltages to get any results. And now one more thing, the growth rate. On the right, this is also well-known, a published diagram that from the 1990s. As you can see, the growth rate of the electrical trees, by the way, is accelerated at higher voltages. By the way, I have to point something out. There's one mistake in this diagram. When I made this diagram this morning, and I inserted it in the presentation, for some reason, the database that lies behind these data points pulled the 50 hertz growth rate up. This green triangle over here at operating voltage is somewhere down here, okay? Because otherwise it wouldn't make sense to test, because you could let it sit at 50 hertz or 60 hertz and without ever doing any tests. So you have to think this triangle here, this data point belongs down here, okay? But you can see the VLF is accelerating at 0.1 hertz. So this is why it's a valid test. If you take 1 hour, you can actually gain something by accelerating the failure mode, the electric trees. Another thing that you can see, and I will elaborate on this a little bit later, if you reduce the frequency, which IEC doesn't allow based on scientific publications, but IEEE does, because that was some of the manufacturer's requirements when the IEEE standard was made. it is not the same. You can see the growth rate is very different. And pretty much what you can take from this diagram is that, testing at reduced frequency is or should be avoided at all costs because it is not the same test. It is not stressing the insulation the same. And technically, there is a recommendation in the standard to extend the testing time when your frequency is lower than 0.1 hertz. But a lot of people in the real world don't even do that. So you get a reduced amount of cycles anyhow. Because just as an example, when you say you want to test the cable for an hour at 0.1 hertz, if your test set cannot charge the cable and you go to 0.01 hertz, then you're supposed to extend the testing time to 10 hours, factor 10. And pretty much nobody would do that, not even at 0.05, which would require double the testing time. But on top of that, even if you would do this, it's still not the same dielectric stress as if you would test at 0.1 hertz. And another thing I just want to point out as a little treat or teaser for the other two parts, if you do, or if you ever consider doing PD diagnostics with a power frequency source, 50 or 60 hertz stiff, and you test at approximately 2.5 to 3 times U0, this is extremely dangerous because you can see the electric tree growth rate goes up here exponentially. Look from this is millimeters per hour here. You go from 1 centimeter or something to a meter and more. So if you would do the PD diagnostics with the continuous power frequency waveform, and you do it at very high elevated voltages, 2.5 to 3 times U0, you will damage the cable during that. And actually, this is the response we get from more and more utilities when they apply this type of technology. Afterwards, the cables fail left and right. And the reason is in this diagram. I mean, this is nothing new. This is published since many years. Why that continues 60 hertz when you do the PD diagnostics, why that causes problems because of these water trees that you grow. So another thing that is hidden in this diagram, see, it's a very potent diagram, is the non-equivalence between RMS values and peak values. And that ties into this thing between IEEE versus IEC, because the IEEE values, they are outlined around peak values. Pretty much they say peak is equivalent to RMS. And so for this example, 3 times peak is only approximately 2 times RMS. Okay, so if you say I do 3 times U0, but you use peak values, the approximate equivalent RMS value is only over here. And again, then you're not doing really a proper withstand test, a demanding test, a demanding stress test to the insulation. And just to clarify this, these diagrams, this study here is one of the base scientific documents of the IEC standard. These values are all in RMS, so this means 3 times U0 RMS. And then over here, just I found 2 pictures that show what the difference is when you have 50 hertz. You have this tumbleweed kind of treeing, and the VLF canal mechanism. So right, it's VLF. On the left, you have this tumbleweed structure, and this is what explains also the acceleration of the VLF of the electrical trees, because the gas pressure is not forming this very distributed, concentrated bush type of structure. It's a very straightforward progressing failure mode when you use VLF, and this is why the test is effective. So now we come to this. Now you will say, what the heck is this? This is a shipyard, right? Yes, it is a shipyard. It's a naval yard, and this naval yard is called HDW, or let's say HDW, as it's pronounced in German. And there you can actually see the origin of the VLF technology. So now how does this fit together? Well, HDW was a naval yard, and they had an electronics department, HDW Electronics. And one of the nice things about HDW Electronics was it was a small research arm for the naval yard, and they are also, as you can see, those are hydrogen fuel cell state-of-the-art submarines. They were involved also in all kinds of big projects and even defense. So there was no budget restrictions for R&D at HDW. So essentially, HDW was the most innovative company in the cable world over decades. Also, when you think about fault location, the arc reflection method is patented by, or was patented by HDW. They invented this in 1960, and it was patented in 1965. Cable radar, TDR, was also co-invented by HDW. And at one point, a few years ago, they had over 60% of the global market in fault location, for instance. Over 50%, actually close to 60% global market share. It was the innovator. And so how does this fit together with VLF? Well, the original VLF technology, the cosine rectangular technology, was invented by Mr. Eckhard Lehfeldt, working for HDW Electronics in northern Germany, Kiel. And the patent for VLF was issued in 1986, or it was issued earlier, it was granted in 1986, and then they also filed the patent in the US. So when some people think VLF is a new emerging technology, this is not the case. VLF is, at least, you know, outside of North America, around since the 1980s, okay? So we're approaching almost, you know, 30, 35 years of VLF testing experiences and VLF testing. And what Mr. Lehfeldt actually did, he came up with the cosine rectangular wave shape and the test sets that can produce that. And so what his thought process was to get to this wave shape, which I will show you in a second. Okay, so what are requirements for field testing? You need a low power equipment because you don't want to supply the apparent power, the reactive power, which is the main argument against 60 Hertz testing, because the test set is so huge. When you want to charge a cable of a few, 100 meters, of a few miles, of a few kilometers at 50 or 60 Hertz, you want low weight, so it's portable, it's compact, it should be able to, be transportable. So the key is frequency reduction. So frequency reduction to 0.1 Hertz, because that makes the test set 600 times less, demanding in apparent power, or 500 times in 50 Hertz. So then the question was, okay, my wave shape that I want to invent should not overstress the insulation compared to an AC test. And you have to know AC testing, 50, 60 Hertz, is typically done at 2 times U naught. That's pretty much across the board in any standard. If you do a 50 Hertz high pot on a piece of equipment, it's at 2 U naught. So 2 U naught, the peak stress, okay, the highest voltage value that the insulation sees is actually 2.828 times the operating voltage. That is the RMS converted into a peak value, so times square root 2, or 41% higher. So, and Mr. Lehfeldt pretty much designed the wave shape that he wanted to achieve in a way that its RMS value was very close to the peak stress of the AC test. And this is where this 3 times U naught comes from, because the difference between, peak of 2 times operating voltage and 3 times RMS is marginal. You can see 2.828 versus 3. So this was one of the main thoughts. The wave shape should not cause a higher peak dielectric stress in the insulation. And then also, I need an AC test set, so I need positive polarity, negative polarity. How do I achieve this polarity reversal? And I want to achieve this polarity reversal very, very steeply and quickly. So at least during the polarity reversal, I expose the insulation to the same stress as a 50 or 60 hertz power frequency voltage. The difference is in VLF at 0.1 hertz, it happens, the zero crossings, it's, 3 zero crossings every 10 seconds. So you start at 0, then positive polarity, 0 crossing, negative polarity, 0 crossing. So, and at 50 or 60 hertz, you have 120 polarity reversals or 100 polarity reversals per second. So it's much faster. But the cosine rectangular waveform mimics the slope. So at least when you transition from plus to minus or minus to plus, then the insulation is stressed in the same way, and the physics is the same that happens in the insulation. And this was realized with an inductor capacitor resonance, which also allows a cosine rectangular test set to recuperate approximately 90% of the energy. So you charge the cable in into one polarity, and when you reverse it, you recuperate 90% of that energy, and you use it to charge it into the opposite polarity. So this is very, very efficient. And you do this by integrating an inductive reactor in the test set that resonates with the capacitance of the cable. And because it's also resonance, it's a very smooth wave shape. It's not a rectangular wave shape. It's free of any kind of switching harmonics, switching transients, because a typical rectangular wave shape is done by chopping, and switching sources with power electronics means. And so to speak, this cosine rectangular is kind of like the real power engineering for real men, right? So it's an inductive capacitive resonance. So this is what a real power engineer wants to see, right? And I just copied you the patent. So if you are interested to read up on that, patent issued, that's the US patent. And for the cosine rectangular test set, Mr. Eckhard Lehfeld working for HDW Electronics, a shipyard. So this is the wave shape, okay? So you have a DC-like plateau, a dwell time. Also, during the end of this plateau in the last second, it is possible with a still patented technology to measure the true leakage current, which you cannot measure with the sinusoidal wave. And then you have the steep polarity reversal into the other polarity. And if you blow this up, you see when you have the 50 hertz reference that the slope of this polarity reversal is similar to power frequency. So this is the original VLF as it was invented in the mid-80s. Just a few benefits, these test sets initially came with a very high test capacity from the beginning, and also the most powerful VLF test sets that you can purchase. For instance, a test set with 25 microfarads at 0.1 hertz at 60 kV RMS. That has to be a cosine rectangular test set, because such power, we're talking something like 8 kVA apparent power, input power, it's not technically feasible with sinusoidal. You have the fast polarity reversal, which will be important in the second part of the webinar series, because as you will see there, the slope is very important to be able to use VLF for appropriate PD testing. If your slope is very little, like your voltage gradient dV/dt, then you do not reproduce proper physics to have appropriate PD measurements. Then you can measure leakage current, and you can conduct a monitored withstand. So you do the VLF test, and you with the slope technology, you can do an accompanying PD trending during the acceptance test, for instance. And then you have the sinusoidal test sets. These have also advantages. First of all, if you want to do 10 delta, you need a sine wave. This is why we, as a manufacturer, just don't make cosine rectangular test sets, but also sinusoidal, because there is an application for it. Size and weights are typically of an advantage. This has partially also to do, unfortunately, with the IEEE standard, because you saw with the numbers that it is biased towards the sinusoidal wave shape. and it allows to get away with much lower test values compared to IEC when you do a sine wave test in an IEC, and that makes typically the test sets smaller, so you can come with, so to speak, one power class less to do the testing, and even up to 62 kV peak, which is the test value for the 35 kV cable, you get a fairly compact and small test value. The disadvantage is the voltage gradient. It is very slow, and that causes performance issues for if you use it for PD testing. So yes, you can do PD diagnostics with a VLF waveform, but you have to make sure you understand the differences. There's two VLF waveforms, and the statement that it is not really producing results comparable to a power frequency like test set is true only for the sine wave, not for the cosine rectangular. And then I compared the waveforms. So you have your cosine rectangular waveform, and now this is how IEC defines the test for the sinusoidal test set. Again, remember, IEC, everything is in RMS. And that means if you want to use a sinusoidal test set, you have to do the test at such a test value. The RMS value needs to be the same as the cosine rectangular, which means the peak will be 41% higher. So that means if you come to a 20 kV cable where the operating voltage is 12 kV, and you do an IEC test, which is 3 times operating voltage, which puts you at 36 kV RMS, the peak of the sinusoidal test set will be 41% higher than that. So you have to multiply 36 times 1.4 roughly, and that is your peak stress in the insulation. And now in comparison, this is what IEEE did. And you can see a drastic difference because in IEC, the energy that you put into the cable, that you pump into the system, is still the same because RMS is RMS, but an IEEE is not. So you can always argue that from a perspective of a withstand test, where you want to properly stress the insulation to really find the critical defect, it is an inferior test because the energy is not comparable. And the growth rate of the trees is a function of the energy, actually. And here one of the practical examples. So this is the second big international study done for VLF. So Dortmund was the big one, the kickoff that everybody implemented in their standard because it was so substantial and took them so long and it was so exhaustive. And around a few years later, Malaysia, TNB Distribution started to do a similar test program, and they tested, as you can see, in a very big number of circuits, more than 17,000 VLF tests. That is way more testing than, for instance, IEEE did to determine their numbers. And they had a certain failure rate. And as you can see, their system, they applied the VLF test, and only 12.5% of the circuits failed initially. So this is not a destructive test. If only 1/8 of my population fails after I switched from a reactive to a proactive maintenance approach, from run to failure to actually we got to do something, that is a pretty good number. So statistically, they ended up with pretty much the same numbers as Dortmund. So it was a very, very successful and positive verification of the Dortmund numbers, because in total you can see on average only a little bit less than 3% of the cables actually failed. There's a difference between PILC and XLPE. So you can see that the PILC cables, or it's actually when you look into the paper, because they published these numbers in a paper. By the way, Mr. Moe, if you ever want to look this up, M-O-H is the spelling, Mr. Moe. Then you can see that the PILC and the mixed numbers, so that means XLPE with some sections of PILC still are, more than 2 times higher in statistically risk of failure than pure XLPE. Another thing that is very interesting about this study, because they did it with a sinusoidal test set, then What they also did, a certain percentage of the cable population was tested at reduced frequency. Remember, not like less than 0.1 hertz. And what Mr. Mo pretty much, said in this paper and this publication, that this should be avoided at all costs. It's not comparable because the failure rate after testing of all the circuits that hadn't been tested at stiff 0.1 hertz was much higher. Actually, this is also the only international study really that that has a significant impact that ever looked into details between the frequency. So it's the best we got. And Mr. Mo pretty much stated that if we tested a circuit that we could not hold at 0.1 hertz, that circuit was at least 3 times as prevalent to fail after testing than the circuits that we tested at 0.1 hertz, which is another encouragement and a verification of the IEC rule of the strict requirement. You need to do it at 0.1 hertz, and if you cannot do it, you need a better test set. That's pretty much what IEC is saying. They take a technical and scientific stand saying, well, you need to bring a proper test set so you don't deviate from 0.1 hertz. And pretty much this study in Malaysia is, kind of the statistic proof that the failure rate is higher. Now, really quickly, to get to an end, a little outlook on the diagnostics. So VLF just to withstand, pass, fail. What will be covered in parts 2 and 3. So first of all, to get the complete picture is always a holistic approach. You need VLF, 10 delta, and PD. And for instance, you cannot substitute 10 delta with PD. Those two methods, they ask different questions to the cable. You get different answers. And only when you do all 3, you get the complete picture, because the VLF is taking care of the local critical weak spots. The PD testing is revealing the workmanship issues in the accessories, and the 10 delta is the test to gauge the aging condition of an XLPE insulation. For acceptance testing, again, which is also the latest trend in Europe, that's the hot topic, monitored withstand test, cosine rectangular VLF with accompanying partial discharge trending. That is, in the process of being the acceptance test now in the IEC world. And then just to give you an overview with the different problems you can have in a cable, joints or splices, you have the local weak spots, the insulation degradation, and then the terminations. The 10 delta is the global test, and the PD testing is for the localized issues. And while the 10 delta is also not able to localize because it's an integral measurement, you're integrating over the entire insulation, the partial discharge diagnostics will be able to pinpoint the problem. This is an overview, and again, most of this will be covered in part 2 and 3. So just to summarize, VLF withstand testing in a nutshell, it's an overvoltage test, like a high pod, to test for good insulation. You carry it out with AC, preferably, or strongly preferably at 0.1 hertz. It is a non-destructive test. You can use it for acceptance test and maintenance testing. To ensure, especially during acceptance tests, the operational, integrity. So if you switch on, nothing will explode. So if you pass a VLF test, it's kind of a safety test. Will it find all the defects? Obviously not, because some of these defects, specifically in the accessories, they take sometimes months and years to grow. That's something for the PD, which the PD diagnostics will make visible. But if you have very severe workmanship issues, then this will fail during the VLF withstand as well. And then as a maintenance test, obviously, you have the cosine rectangular technology, which has its benefits. You have the sinusoidal technology, which has its benefits. For withstand testing and accompanying PD testing, the cosine rectangular is preferred. You always apply the test over an extended period of time. That means don't cut it short. Go, especially on service age cables, the full hour. It's governed by various international standards. There are unfortunate differences between IEC and IEEE, and the result is a go, no-go. It's a pass or fail if you do it as a pure withstand test, okay? And just to summarize, again, it's effective to replace the DC testing just as an after repair test. It is the tool to get the reliability numbers up, because you rake out these critical defects, these critical electrical trees. And as a monitored withstand, it has benefits as a predictive test. And it all ties into how do you do a successful cable program. You identify the scope of your program. You identify the cable population that you want to test. You need to test it. That's the practical component. You should consider always, if you have a fault location database, so you have an understanding of this circuit already failed, this circuit is new. And then always keep in mind, certain test methods are not always applicable for everything. Again, holistic concept, you need all three, VLF, 10 delta, and PD, because certain methods, specifically the global methods, one of them is the 10 delta, cannot be applied to certain types of cables and never really to mixed cables. Okay, I guess just really quickly on our products, I just picked some so we have solutions for that as well. On the left, you see a classic small sinusoidal test set. On the right, you see, kind of the silver bullet. It's a unit that has all waveforms built in, the sinusoidal VLF for the 10 delta, the cosine rectangular for the withstand, the long cables, and the slope, the monitored withstand, and also what's called the dampened AC for the pure PD diagnostics, which will be covered in the second webinar in April. So it's an all-in-one unit that can do everything. And now we will go to the question and answer session. I will be one of the panelists, and I have Jason Sauchek with me, my colleague, my applications engineer colleague from NAFTA days, and we will be happy to answer your questions. So I will give it back to Greg.
All right, thank you, Robert. Like you just mentioned, we'll take about 30 minutes to answer as many questions as we can as possible. So if you have any more, you can go ahead and submit them into the Q&A box. For those of you that are leaving, when you close the webinar window, you should see a survey pop up on the screen. We would appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve our future webinars. On the survey, there's a field where you can also request a demo or quote on with any of our Mega products. A copy of this presentation, along with a link to the video recording of this webinar, will be emailed to everyone within about 2 business days. You can also view previous webinar recordings on our website at us.megger.com/webinars. And you can also register for our upcoming webinars, which the one coming up next month is primary injection testing of low voltage circuit breakers, which is taking place on January 18th at 10 a.m. All right, now let's get to your questions. First question we have up is, what do you mean 10 delta is useless for acceptance testing?
So should I answer that or you answer that?
I can take that one.
Okay.
So I think that what Robert was saying is that 10 delta is a test that looks for aging conditions on the cable. And when you put new cables into the ground, it's impossible to have aging conditions on them. So when you do the test, you say, what am I looking for? I'm looking for something that can't possibly be there. I'm looking for aging on new cables. It's not possible. The other part of the equation is that from the manufacturing process, there's still outgassing from the cables, especially on the extruded type cables, that will affect your 10 delta reading. So your first reading for the first couple of years may not be representative of the cable. It takes a little bit of time for those gases to escape and for the 10 delta to stabilize. And if you took that 10 delta test right away, you'll see that your first reading was some number, and your reading in 5 years will be a improved number, a lower number. And you'll be sitting there scratching your head going, what's going on? And it's because these gases were present at the time of the first test. Do you have any other comments on that?
Well, that's pretty much what we are told by our customers all the time. I told you recently the latest example was the guys in Slovakia, they don't do any 10 delta testing until the cable is service age, and they established for themselves the age of 7 years. They don't even bother looking at it because they did it in the past and they were misled. And actually, just on a side note, at the upcoming NITA conference, okay, next year in March, we will have a diagnostics seminar, and one of our leading diagnostics experts will be there as well doing a presentation, and he will bring a few case studies, or let's say case studies, examples that we got from the customers where they did a 10 delta as part of the acceptance test, and they were misled by it and made let's say very poor decisions based on that, and ended up kind of hurting themselves more than actually what they gained from the 10 delta test, because they started reading more into it than they should have, and it ended a little bit in a medium disaster. So it's pretty much, if you ask any experienced utility or service provider that ran into this, what Jason perfectly described, that you have these chemical settling processes for many years, you will get incorrect readings for the initial stage of life of the cable. So, and again, the aging condition is the water content, the water treat content in the cable. If it just comes out of the factory, there is no water treating in the cable, because you need very, very long, and again, AC voltage as an ingredient, moisture and time to establish these water trees. So what are you expect to measure? Like nothing. You will measure at best a perfect cable. Okay, so it's pretty much a useless acceptance test. That's kind of like what the industry understands these days.
All right, we have a lot of really good questions here.
All right, so we're gonna take another one. Next one is, in cable, what test is better, offline VLF PD or online PD?
So the trouble with online PD is no matter how good of a friend you are with the system operator, you can't get him to change the operating voltage for you. With offline PD, you can change the voltage up to, typically up to as much as twice operating voltage. And that gives you a lot of predictive power. So when you go to online testing, I can only screen for PD at operating voltage. That's it. That's the only option I have. And it's kind of like taking a picture. I can say, in this intersection, there's currently no cars here. In this cable, there's currently no partial discharge. It has very, very little predictive power. With the offline PD, it's like going to that intersection and looking left and right and saying, well, there's no cars in the intersection right now, but there's a car coming towards it and it'll be here very soon. By being able to adjust the voltage up to twice rated voltage, I can get that predictive power. So online PD testing to me is nice for an alarm system if it's continuously monitored. If it's the type of thing you do only periodically and once a year or something, I don't really see the value in that. The offline testing is much better for predictive testing.
Yeah, I mean, the question is interesting because everybody asks this, and I think the proper answer is, it depends, typical engineer's answer, right? It depends. It really depends on what you want to do, because monitoring is something completely different than trying to do condition assessment. Monitoring is not there to do condition assessment. It's just establishing a baseline, and you're looking for any changes, and then you have an emergency time frame that you can still act before something really severe is happening. It comes from the world of substations where you have online monitoring of concentrated assets. It's not really that common on cable, especially on long cables. And for the cable world, really the offline testing is the way to go, because to go through all of these efforts, just to get some, monitoring information, this is not really the goal for all these efforts. Like, you want to know what is the condition of my accessories, which means splices and terminations, and the aging condition of my main insulation. And to do this diagnostics, you need to be able to vary the voltage, to identify that. And so both methods have their benefits. It depends on where you apply them, what you're trying to do. It's not that online is better than offline or offline is better than online. it's very much the answer lies within the application. So, next question.
All right, next question is, let me see. I couldn't understand how VLF tests are non-destructive, knowing that it forces electrical trees to produce cable faults while testing, if the cable has an existing weakness.
Yes, so again, the definition of a destructive test is you do this with the intention to destroy the sample, and you will do whatever is in your power to destroy the sample. And there is a test for that. There's two types of AC high pods recognized by international standards. One is called a withstand test. You don't even have to be as specific as saying it's a VLF withstand, because you could technically, if you would have the means, also do a 50 hertz withstand test, but nobody's doing that. So it's withstand testing and step testing, and there's two protocols for step testing, and that test really breaks the sample. While the withstand test, if you don't have any weaknesses, the outcome will be a pass. And you saw this in the numbers of from Malaysia, like only an eighth of the cables failed. So it does not destroy the cable. It does not introduce any new weaknesses, which is also the characteristic of a destructive test, like of the step test. You will stress the cable until you will produce new weaknesses that will fail the cable. And the VLF test is not doing that. It only accelerates what is already there. So if you have nothing in the cable, nothing will happen. It will be a pass. So this is why it's not considered a destructive test, because it's a withstand.
All right, thank you, Robert. The next question is, what is the difference between an acceptance test and an installation test?
So fundamentally, it's the voltage that you apply to the cable, and acceptance test is a bit higher voltage than an installation test, but it's also what you're looking for. Per the IEEE, definitions of these, an installation test, you're really looking for shipping damage more than anything. You're making sure that you get a good piece of cable on site, onto the construction site, intact, and that you're not going to waste your time and energy pulling in cable that's already failed. The acceptance test is kind of the final check before that cable is energized. It's the highest voltage that cable should ever see in the field. And it's there to make sure that all, that cable system is in good shape and that it's ready to be energized. So fundamentally a voltage, but also the types of defects that you're looking for would be the difference between those two types of tests.
Yeah, just to add this, the logic that IEEE applied here was the acceptance test, as Jason explained, is kind of you do the test and then you throw the switch, and nothing should happen if you pass the acceptance test. The installation test was introduced there because it is the last chance for you to test the cable just as is. Because just before you start putting your hands on it, like just before you start mechanically and electrically changing it by putting on terminations and splices, just the cable by itself, the installation test is supposedly the last test where you have the chance to catch any defects before you start building the whole circuit. Now, unfortunately, a lot of people are skipping that, which, they skip it. That's all we observe in the field. Is that a good thing? Probably not. But a lot of people feel they don't need to do the installation test, which is kind of, kind of sad because it's in the standard for a reason.
All right, the next question is, when the dielectric starts developing in water trees, is there some type of discharge that could be detected? Has there ever been a signature recognized that would show damage to the dielectric?
The water trees don't exhibit any discharges. The tan delta test is there to detect the presence of water trees, and what they're doing is degrading the quality of the insulation and allowing more resistive current to flow through the insulation material. So we can detect the presence of water trees in that manner by measuring the resistive current and the tan delta test. But there's no partial discharge test. Once the water trees get severe enough that they become electrical trees, the electrical tree will create a signal that we can detect. and that's I'm sure will be covered in the partial discharge webinar coming up. But they are different signatures, different types of tests, and completely kind of different phenomena, although they are related to each other. So no, to answer the question, the water tree itself does not have any characteristic signal injected into the cable. It's just the fact that it's weaker insulation at that point.
Okay. The next question is, someone noticed the testing time is 30 minutes in the IEEE guide. Does that fall into this category of compromising test times?
Okay, this is like, it's a little bit of a convoluted issue. First of all, you have to be careful what you're talking about. Acceptance testing or maintenance testing, okay? So for maintenance testing, they say 30 to 60 minutes for, with recommendations for 30. IEC is just strict. They say 60 minutes on service age cables. And now on the acceptance test, initially, in the IEC world, it was 60 minutes as well. And in the main standard, it still is. However, there's a second IEC standard that is specifically mentioning the acceptance test. And for the acceptance test, they also require, again, 3 times U0 RMS for 15 minutes. And the reason for that is the industry learns. And specifically in Europe, I don't know the exact reason for that. It is kind of an observation, you know, that people make. It looks like that the overall quality of the cable circuits is higher and the overall quality of the cables. Also, IEEE, the database numbers that they used for writing these standards, there's a few diagrams in there that show survival rate of a population over time for many different utilities. And except maybe 1 or 2 cases, all of these numbers were drastically below, for instance, German or Southeast Asian numbers. So when you look at the survival rate over time, up to 60 minutes, the curves from the U.S. utilities that took part to provide the database for the IEEE were much less. So overall, the cable circuits in the U.S. were in a much worse shape. So over time, what was found is that most of the failures on an acceptance test, remember, there is no water trees in the cable, it's just an acceptance test. It fails within 15 minutes or it's good. The reason is the VLF test can only make severe workmanship issues flash over. Everything else, you do a partial discharge test to actually reveal those conditions. Let's say improper splicing, you know, you do the PD test and the splices light up like a Christmas candle. You see this with a PD test. The VLF test is there to find the gross defects after installation and just to make sure that you have, you know, as I said, operational integrity. You throw the switch and nothing explodes, right? Because the cable passed the test of 3 times operating voltage. So it depends on what you're doing. One very interesting thing on the testing practice, the Europeans, since the VLF testing started, they in some cases deviated from this 3 times U0 from the voltage level. What they never compromise on is the testing time. So when they do a VLF test on the service age cables, they do 60 minutes, no compromises there, but sometimes they reduce the testing voltage as low as 1.7 times U0, and they do it for a reason. They typically have a track record of the circuits if that cable has failed before, and whenever they VLF test a cable that has already been on record for previous failure, they will not apply 3 times U0. Because remember, service age cables probably a high water tree content. If the 10 delta is really bad, then what is the expectation if you do a full-blown VLF test? The expectation is pop, 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 pop. So to avoid that, they have to cover the fault that is most common on these systems. And if you think about a 3-phase system, the most common failure in a 3-phase system is a single-phase ground fault. And that means the other 2 healthy phases are elevated to the phase-to-phase value, from the phase to ground or line to ground to the line value, which is a factor of √3, which is approximately 1.7. So when the Europeans test very, very old cables that have prematurely failed, they have a track record, they probably go only to 1.7 or maybe 2 times U0 for 60 minutes, because then they know if the cable passes, I know if there's a ground fault in the circuit, at least the cable will not immediately fail. But on the other side, if you have that much of an old cable, most likely the 10 delta is really bad, and then you elevate this in your list of cables to be replaced with a high priority. You really try to give this cable a priority, because sooner or later it will fail. So that's the difference in testing practices.
All right, next question. Would you recommend to make it a standard to do a VLF on aged service cables in addition to the insulation resistance? Is that because VLF is better on flashing over pre-existing trees, which might not be captured on insulation resistance tests, which could be more common on older service cables compared to newer ones?
So yes, the direct answer to this question is, would I recommend VLF testing service age cables? Yes, that's the maintenance test values in IEEE. That's what they're there for. In relation to the insulation resistance test, you're looking for different things in a lot of these cases. There's a lot of things to kind of unpack with this question, but yeah, the VLF test is going to give you a lot of confidence that that cable will stay in service in the case of a ground fault like Robert was describing, or a lot of confidence in the overall quality of that cable, where the insulation resistance test, maybe less so. It doesn't put as much of a voltage out there. If you're concerned about the water trees, as this person questioning is, flashing over pre-existing trees, that test is 10 delta, which is going to be discussed in an upcoming webinar. That's the test that we use to discuss the 10 delta, the water tree content.
All right, I've seen this question come through a couple of times. Is it acceptable to test more than one cable at a time?
Yes, surely. Actually, this is the big benefit of having a large capacitance test set. If you're just after the VLF test and you don't try to turn it into a predictive test or gather more diagnostics information, it is actually the common practice around the world to parallel the 3 phases and get the VLF test out of the way. And only if it fails, then you have to do further investigation. Okay, now I have to find out which of the 3 phases failed, and then you do fault location and you proceed. But yeah, that is pretty much doable. It's recommended to save time, because you cut the total test time down from, let's say, 3 hours to 1 hour.
As long as it's within the capabilities of the test equipment.
Yes.
So especially with the sinusoidal units, there's a maximum test capacity based on the total length of cable and the capacitance of the cable. There's a maximum test capacity that the sinusoidal test unit can energize at one point. So if you parallel 3 cables, you put 3 times the length of cable on that VLF test unit, and it may exceed what that sinusoidal unit can test. When you go to the cosine rectangular technology, that has, dollar for dollar, about 10 times more power than a VLF sinusoidal unit. So you can test about a 10 times longer cable with the same approximate size machine, same kind of power supply. So you can get into testing much longer cables with the cosine rectangular, even parallel. So yeah, it's perfectly fine to do that with VLF testing, as long as you're within the power capabilities of the VLF test unit.
All right, next question. If you have an aged in-service cable with some water treeing, will VLF accelerate the minor water treeing, or will the electrical treeing not affect the water treeing? Or likelihood that the water tree will now form the electrical tree?
Okay, so the way this works is, again, the acceleration happens only to the electrical treeing. The water trees are not affected. They grow by themselves in service. You have 60 hertz applied operating voltage. Let's say you have a 25 kV cable, operating voltage is 14.4 RMS, and the cable sits there and sits there and sits there. Over time, with the 3 ingredients, AC voltage, moisture, and time, these water trees will slowly form. And now with the latest generation cable, the tree retardant XLPE, which was introduced in the early 90s, and the EPR, by the way, just to get this out of the way, EPR is also treeing as much, it's comparable to tree retardant XLPE, the tree rate. And so these trees will grow over time naturally if you have moisture in the cable. So the trick here is why VLF testing is so effective. Now you apply the voltage. If none of the trees is critical, let's say, I don't know if you can still see the screen, but if you remember back this picture, on the left, you have these, very uniformly distributed trees. None of them is a critical tree. During a VLF test, none of these trees will will cause a problem at that precise moment in time. Now you come back maybe 5 years later or 3 years later, and then these trees will have grown under service conditions. And now maybe under VLF stress, some of them will form electrical trees. And then you have to apply the voltage for long enough to grow these electrical trees to make the water tree blow out, to cause the failure. This way, you avoid that this water tree keeps growing into a critical tree in service and then fail the cable in service. So the water treeing is happening no matter what. And again, with the latest generation of polymer cables, it is very slow, okay? Compared to the original polyethylene cables, PE cables, treeing is minimal, but it still happens over time. It just takes very long. At the VLF, it stresses the insulation, and if there is no critical length water tree that could cause a conversion to electrical tree, nothing really will happen during the test. And then you come back, and maybe nothing happens the next time, and you come back, and maybe nothing happens the next time. And then you come back to the cable and you might get a failure because over time, the insulation now has aged enough that the water tree content is so high, the length is very high, and you've got 2, 3, 4, whatever critical length water trees. And within the 60 minutes, you will flash over the most critical ones. And then you come back after 2 or 3 years and repeat. And this is kind of a little bit of the price you have to pay for the proactive maintenance. It's a hamster wheel. Once you start, you can never get out.
All right, the next question is, can you explain the usefulness of monitoring leakage current when conducting acceptance testing?
I'm sorry. I'm going to just talk briefly. I'll let Robert answer most of this. But it'd be like monitoring leakage current on a DC high pot. You can watch your leakage current going up during the time of the test, and if you start seeing a trend, that gives you the indication that there's a soon-to-be fault, maybe something that isn't actually going to fail the cable under your hour, but gives you the opportunity to extend your test time out and try to cause that fault to fail under your test condition. It's also able to detect certain types of weak spots in the cable, such as something like water trees. That's more of a resistive type of fault than a capacitive type of weak spot. But I can see Robert over here chomping at the bit to answer more.
No, not at all. No, actually, what happens when you do the leakage current trending, again, it's a trend, okay? Yeah, you have to look how it changes over testing time. Well, you have 3 scenarios, right? You can have a decreasing, increasing, or a stable leakage current, okay? If it's increasing, there's probably a low resistance fault somewhere that is, the cable might hold the voltage in the testing time, but the leakage current goes up, and there's a condition. And actually, there's a few utilities in the US, they have a disqualification criteria that when they do the VLF test, because only with the cosine rectangular VLF, and they have a cosine rectangular test set, only with that technology you can also record the leakage current during the acceptance test. When the cable hits a threshold, a number that they know from that they have found by experience or by a study that they conducted, they will disqualify the circuit as well, even though it did not directly fault during the test. But the leakage current is so high that there is a low resistive problem imminent. The other thing is if there's any like moisture in the cable, the leakage current will also trend differently. And if the cable is good, the leakage current will just go to a certain level. So the and it should stay there in a stable manner over time. And this is how you utilize the leakage current. So actually, when you ask this question, from an acceptance testing point of view, the best monitored withstand is VLF with leakage current trending and PD trending. That would be the silver bullet, where you see the high resistive faults in the accessories, you stress the insulation enough to have a withstand test, and you monitor the leakage trend, or you trend the leakage current, I should say, and that gives you all the information to assess the cable during acceptance testing.
Now, what kind of a test set measures leakage current accurately?
Only the cosine rectangular, because for the sine wave test sets, it's not defined. It's very easy because the waveform is changing at every single point over time, so there's not really a leakage current defined. The test sets, however, they give a current, but that is the total current. The leakage current is only a small part. So to be very honest, if you want to do this, you can only get a test set from us, because also the leakage current monitoring or measurement is a patented technology. So we still make cosine rectangular test sets, and the leakage current measurement circuit in there is still an active patent, an active worldwide patent for that.
All right, next question. Please tell me why the 60 hertz test set uses 600 times the power.
Okay, that question's incorrect. I'm sorry, the way it's, the VLF test set uses 600 times less power than 60 hertz.
I might have misspoken, like less power, yes.
Okay. Sorry.
Because just engineering answer, the apparent power S, is the frequency is in there. It's times frequency or times 2 pi the frequency. And if you reduce the frequency, then you reduce the apparent power or the reactive power that you have to supply. So frequency reduction is means you're shrinking the test set to field test size.
All right, next question. One of our attendees has given us a scenario. So a customer has specified VLF, PD, and 10 delta for commissioning tests of cable that they've installed. Do we really have to do all three? And if not, which ones should we recommend? Do we recommend that they do?
As we've talked about a couple of times throughout this Q&A session, 10 delta on new cables, commissioning testing new cables, is maybe not so valuable. The thing you're looking for is aging conditions, and there can't be aging conditions on new cables. So if you're going to skip one, it would be 10 delta. But for new cables, VLF and partial discharge are excellent choices, excellent tests. I recommend them for testing all your new cables. Then when you get to age cables, it really is vital to do all three tests, because you still can have the same types of faults as on new cables, workmanship issues, poor splices, things of that nature. Those don't necessarily go away. But now that cable's been in service for some time, you can have aging conditions on the cable, and that's where the 10 delta test is going to be able to help you. So to expand on that previous question a little bit, even better would be to do VLF, PD, and 10 delta and leakage current. And we can do VLF and PD and leakage current all at the same time with the cosine rectangular waveform. We just have to use sinusoidal for the 10 delta test.
Okay, I think we're going to try and get in one or two more questions. When you find a bad cable, what type of locating would you use if you didn't plan on replacing the entire section of cable?
Well, that is a very straightforward answer. You would just apply the standard fault location technology. So you would go for the arc reflection method, because it's most likely a pinhole fault on a solid dielectric cable. So you use a radar high voltage combination, which has been in the industry, again, HDW patented it in 1965. Now everybody has it under different name. We're still using arc reflection method as the name ARM. And that is good for finding 90% of the faults in a solid dielectric easily. It's a really straightforward method to use and the industry standard.
All right. I know we've gone a little longer than we'd planned. You want to get into 2 more?
Yeah, 2 more questions. Why not?
Okay.
So do you have one? Like which one? So many.
There was one about DC testing and insulation resistance.
Yeah, we should answer that. Yeah.
So I don't remember the question specifically, but it was along the lines of asking about insulation resistance testing, since that uses DC voltage to do the test. How do we square that with saying don't do DC testing on? So the question is, I was told to always do insulation resistance testing first. This being a DC voltage, should this not be done? So that's the actual question. The answer is the insulation resistance test is relatively low voltage. The highest test that we sell is 15 kV DC. And it's also should be done for a short duration. You can do your test for a minute and get useful readings. It's a very good test to do first. It tells you that the cable's in good enough condition to proceed with more aggressive type testing. It's not the be-all, end-all test, but it's a nice, good kind of first screen test. And if you keep your duration short, you won't fall into the problem of the trapped space charges. Those occur after a certain amount of time.
Yeah, exactly as Jason said. When you have to don't confuse things. Yes, the insulation resistance test is a classic DC test, but it's typically most people just do it for 1 minute, right? And that's it. And then you discharge and you're okay. When we say DC testing on cables, they were like standards for that. And the DC was the standard method for the PILT cables, and these tests, they were talking about 30 minutes testing time, and 4 to 6 times operating voltage. So that is a complete different thing than hooking up a little, insulation resistance tester and, just measure some gig ohms, okay?
We run into the same spirit of the same question in fault locating. The first step of fault locating is to do a DC high pop, but I try to avoid using those words. I try to say DC breakdown test because exactly as we've been talking about, the duration is kept very, very short, really 15 or maybe 30 seconds. So there's also a time component in there before these trap space charges become a problem.
All right, next question. I want to make sure I understand correctly. We calculate test voltage at 3 times the operating voltage, not the cable rating listed on the cable?
Okay, this is a very interesting question because it's also unfortunately convoluted because IEEE went rogue with this. The answer in IEC is very simple. U0, the operating voltage, is defined. It's defined as an RMS value and as the line to ground voltage. And there's no discussion about this. And all of these standards are in U0. So all the testing is always scaled to U0. And the standards say 3 times U0 RMS. And because the RMS, as I showed you, the cosine rectangular and the sinusoidal are very different in waveform. But RMS, it is, something that is related to the energy that is going in and coming out of the system. So it's comparable. And this is also, by the way, I didn't explicitly mention this. If you do a VLF withstand test with sinusoidal and cosine rectangular, and you do it to the same proper test parameters, the outcome is the same, okay? It gets complicated when you use IEEE numbers versus IEC numbers, then it's not the same anymore because the IEEE numbers are kind of soft compared to the IEC numbers. When you do it to the same RMS value, the outcome of the 2 tests are the same. The other thing is when we say to the cable rating in the power industry is always a 3-phase rating, okay? So when you say 15 kV class cable, that means the individual cable, when you have 3 of those, does not see 15 kV. That 15 kV is phase to phase between 2 conductors, 2 center conductors. You would be able to measure that. The cable insulation itself sees U0, the phase to ground, the line to ground value. And now here's the problem. in North America, it is very common that people have cables installed and they do not operate them to the maximum operating voltage that the cable could hold. Typical example, you have 25 kV cables in the ground, and because you want to satisfy some over insulation recommendations, let's say at 133% or something, you use 25 kV cable and you operate it at 15 kV. Here it gets really, really complicated, which will be addressed in some of the other two parts. IEC still says all the testing has to be done to operating voltage. IEEE has a loophole. It says you can, for the VLF withstand, deviate from the U-Not to whatever operating voltage you have in place. So let's say if you have a 15 kV cable, U-Not is 8.7, but you operate at 7,200 instead of 8,700, right? That's what a lot of people do, or 7640 or something. Then IEEE lets you adjust the values. IEC would not. So you really have to be careful what you're doing there, or you have to at least write it down, and you have to find kind of your own test program, and you can use the IEEE guide as what it is, as a guideline. So the world is in this case much easier in the when it comes to IEC, because it's always U-Not. Whatever you do, you calculate your operating voltage or your what is supposed to be, and then you take a multiple of this. This is why it's very easy. You don't need a big table to do that, like in IEEE. But yes, the answer might be different in IEEE because you are allowed to deviate. Now, interestingly enough, when you do the 10 delta test, then also in IEEE it is U-Not again, and this can cause the paradox situation under certain circumstances that the 10 delta in IEEE can be carried out at higher voltages than the actual withstand, depending on which numbers you do. I mean, this should be avoided, but it's possible to get there. While IEC, no, it's U-Not, and the 10 delta is what you do. Half, 1, 1.5, and 2 in that times of U-Not, and the withstand is 3 times. So much easier. But yes, it should always be to U-Not, which is the rated phase to ground voltage.
All right. Thank you, Robert, and thank you, Jason. Yes?
Just saying thank you.
Oh, well, thank you. It looks like that's all the time we have for. We apologize if we did not get to your questions today, but we will make every attempt to follow up with you in the next couple of weeks offline and get you the answers that you were looking for. We'd like to thank you all for attending the webinar today. And if you can remember, please answer the survey as you exit the webinar today. The survey also includes a field for you to request a quote or a demo if you're interested in something like that. Thank you all again for attending, and have a great weekend.